Okay, so intermolecular forces, as we're talking about it, remember that they are only present with solids and liquids, right? Intermolecular forces don't exist between gases, because that's why they're gases, right? They don't interact with each other. Ideally, yes, that's true. Ideally. Oh, that's a good, ready bonus question. Raise a hand. What conditions of temperature and pressure make a gas ideal?
Oh.
Quatley, what is that? High temp? Low pressure. Good, you can have a smiley face, Quatley. Okay, so this state, remember we talked about how to change?
When they're going too fast, they just miss.
Yeah, because they don't have that chance of interacting. So when you think about solids and liquids and gases, right, change your perspective of what those things are. Okay, relate them to the interaction between the particles and the energy, right? Solids have very low energy, they're just vibrating and spinning, but they have extremely strong forces. Liquids also have pretty strong forces, right? A little more energy, because now they can flow freely. And then gases have a ton of energy, but really no forces between them. Okay? So that force idea is kind of the whole part.
Forces between them or forces that like it can push on stuff?
Forces between the molecules. Okay. Yeah. So remember, and I think I'll have a picture here, remember that when we talk about intermolecular forces, it's about, so like a water molecule, right? This right here, that's a covalent bond, right? What I mean by an intermolecular force is the force between two water molecules. That's what this whole chapter is about, right? Is this force. It'd be like if each of you guys were a molecule, the force between you, not the force it would take to pull your arm off. Okay? All right, so if we're thinking about it in a sense of force and energy, the whole way in which to change a state of something is by adding more energy, right? If we add more kinetic energy, or we remove some of that kinetic energy, that's how we get something to change states. On the same note, and we talked about this before with a vacuum, you can also do it with pressure, right? How I talked about if I had a vacuum chamber, I can put a beaker of water in there, and if I take out all the particles, so there's no pressure on it anymore, you can get the water to boil. Even though its temperature is still at room temperature, right? So that combination of pressure and temperature allows you to disrupt those intermolecular forces a little bit. Okay, so the strength of an intermolecular force varies over a pretty big range. The goal of today is, one, that you can identify what force is present in a molecule. I give you a molecule and say, oh, that has hydrogen bonding, or that has dipole forces, okay? And then secondly, to relate those to explain why certain things happen, like boiling and vaporizing and things like that. So intermolecular forces, like we said, are between two different molecules. This, the covalent bond, is often called the intramolecular force. Right? So an ionic, metallic, or covalent bond are a lot stronger than an intermolecular force. But they can still be pretty strong, as we'll see. But keep in mind that when something boils, when something melts, are we breaking this bond?
No.
What's the force that we're breaking? The intermolecular force. So one thing we'll see often is that the stronger the intermolecular force, the harder it is to get something to boil or to change phases. Okay?
So when the guy was saying when he smashes the ice cube, that's just breaking the intermolecular forces too?
Exactly, yep. Because it's still just a physical thing. You're just causing the water molecules, because when the force is applied, the weaker force is going to give out first. Right? And so these are what break, not this. Most of the time, in order to break this in water, that takes electricity. So yeah, Isaac.
Chemical reactions break the intramolecular forces then?
Yeah, yeah, very good. Yeah, a chemical reaction is always breaking the bond itself. So good.
That's what I thought.
Same. So when we talk about liquids, lots of their properties can be explained due to these intermolecular forces. Such as, in order for something to boil, it has to have enough energy to overcome the force so it can separate, right? Because once it becomes a liquid to a gas, those forces are now gone. So the stronger the force is, the higher the temperature at which the liquid boils. Same for melting points. That sentence right there where it says, so the stronger forces, like highlight that, circle that, that's like key. Because the way that you're gonna see the questions on the AP test is it's not gonna say which of these has the strongest intermolecular force. The question's gonna say which one has the highest boiling point. But in a sense, it's asking the same question, but you need to be able to make that connection that a high boiling point means a high intermolecular force, or a strong one. Okay? The thing about intermolecular forces, we talk about all these three types, is they all are an electrostatic force, or Coulombic attraction. They're all a positive and negative some sort of relationship. It's just that our magnets are getting stronger with different forces. So, Parker?
So is like, so the more polar the molecule is, the more electrostatic it is?
Yeah, so that's going to be a big key as we get into these, that polarity is going to play a really big role in those strengths of the forces. Yeah, no, good point. Okay, so let's talk about the first one. So London dispersion forces, I just call them dispersion forces. It's just kind of what they're called now. They call them London dispersion because they were discovered by a guy named Fritz London. So this is an interesting idea. So what he noticed in a molecule, okay? So I have a molecule of iodine, okay? This molecule right now, when you have two things bonded to itself, is this molecule polar?
No.
Not polar at all, right? Because it's like having a tug of war with yourself. Tupperware. Okay? So right now, this is a non-polar molecule, and that's key. Okay? Dispersion forces exist in non-polar molecules. Okay? And it's the only force. Exist.
Can you have liquid oxygen?
Okay, so if this is non-polar, this was really interesting to people, right? Because they were like, if it's non-polar, how is there any attraction between the molecules at all? So what he found is that as the electrons are orbiting around the atoms, right, as they're bonded, there comes a moment, because the electrons are constantly moving, that the electrons are slightly more shifted to one side, just as they're rotating. And in result, it gives it a slight negative towards that end. And then what can happen is because the electrons have shifted heavily this way, so I kind of think of it as like the cloud is like this, okay, is this can then actually influence its neighbor and cause the electrons to kind of do the same thing. Because electrons are all negative, and so then we get this right here. That's your dispersion force.
At what point
That's
does it
super
become
weak.
polar though?
So it actually does, by definition, it doesn't become polar. Because polar means that in the bond, the electrons are actually truly shifted.
Oh, okay, so it's like a permanent shift in what the probability of where electrons going to be.
Yeah, so this is just like a momentary shift of electrons.
Gotcha.
And so that's why, would you consider this a strong or a weak force?
Super weak.
Yeah, it's really weak. And that's why we see actually most of the time, most non-polar molecules are gases already. Right, if you look at fluorine, chlorine, right, both of those, bromine's a liquid, iodine's the only one that's a solid, but iodine, Eli brought up this topic that I'm still pondering, but iodine sublimates from a solid to a gas, almost at room temperature. And so we see that in general, those non-polar substances already are really weak. And if they are a liquid, we see that they evaporate normally quite easily, because dispersion forces are just barely holding them together. And to make them a solid, what do you think you have to do?
Oh, you have to get it super.
Yeah, you either have to get to really cold temperatures or apply a crazy amount of pressure to make it happen. So, okay, questions on what a dispersion force is? Okay, all right. So with a dispersion force, if we are analyzing two different things and they both have dispersion forces, it's important to be able to recognize, okay, well, which one is the stronger of the dispersion force? So the pattern that we look for here is that dispersion forces tend to increase in strength as the molecules get heavier. Okay, so I'd underline, so that bolded sentence right there, put a star next to it. Okay, where it says, so dispersion forces off to the side of the chart. Dispersion forces tend to increase in strength with increasing molecular weight. So why would that be? Why would a heavier molecule have greater dispersion forces? Any ideas?
There's more electrons.
Yeah, there's more electrons to influence the others, right? So another word that they often use with dispersion forces is this idea of polarizability. Okay, so it's actually, I find it really funny. So one way they actually, in your book, I'm pretty sure it's this book, they describe polarizability is they describe it as the squashiness of the electron cloud. Yeah, they use that word, squashiness. Because what they're saying, if you notice, like in that picture I drew, right, the cloud got squashed to one side.
It actually kind of looked like a squash.
No. It kind of did that. Kind of.
Yeah, I don't know.
A little bit. Yeah.
It looks more like a gourd.
Oh my gosh.
That's true. So polarizability is, the more polarizable something is, the greater its electron cloud can shift. Right? And the heavier it is, we see that. So if you notice the trend, right? So as we go down this group, as they get heavier, their boiling points get higher. Right?
No.
Because that intermolecular force is getting stronger. Okay, same thing over here with just the noble gases, right? Even though they're all gases, we still see a trend that the heavier it is, the higher the boiling point.
Wait a minute, so you can have a gas become a liquid,
Yeah.
like helium liquid.
So helium to be a liquid has to be like 4 degrees Kelvin.
Yeah, helium is, yeah, it's basically almost at absolute zero to get helium to be liquid. But
Hydrogen be a liquid.
What's absolute 0 Kelvin?
with dispersion, it's influenced by weight, right? The heavier it is, the greater the dispersion force, and it's also affected by its shape, right? Because the more it can interact, the more area it has to come in contact with, the greater the force will be, right? So these two molecules are actually, they are called isomers of each other because they actually are the exact same things. They're made of the same number of carbons and the same number of hydrogens. They have the same weight, but the structure of them changes what it is. Right, this is what gets you into organic chemistry. But what I want you to notice the difference is this one has a higher boiling point because of the greater surface area.
Wait, so could you say that the one with the higher boiling point is more like stable then?
What do you mean by
Why
stable?
wouldn't they all just want to have the highest boiling point so it's harder to break them apart?
Why? Say that one
You
again.
don't
So why wouldn't
get
they all just go to the one that has the higher boiling, like creates the shape that has the higher
Oh,
boiling?
so like would this structure be a more stable structure than this one?
Because that one's harder to break apart, so why wouldn't that one just want to do that if it wants something?
Because you gotta remember that
You're
it's
squashing.
between the atoms, right? Why are they bonding? To get their 8 electrons, right? So in both of these structures, the atoms are bonded to 8. They all have their octets still. Because sometimes there's different ways in which it can be done, and it's still just as stable.
Okay.
Like so, the compound like this, if you want to see it like in a Lewis structure, so pentane is 5 carbons, and then it's totally covered in hydrogens on all sides. And then
These other one a carbon circle.
it's, how does it go? I think it goes,
Like, it's just random which one they form?
no, that's not it. How does it go? I can't remember neopentane.
What's that supposed to
Wait a
mean?
minute, and why is the more rectangular one N minus pentate than the neopentate?
So there's a totally different, oh no, I was right the first time. Okay.
I can see the
There's a totally different nomenclature system for naming organic molecules. Wow. So, yeah. So then it looks like this, and then those are totally covered in hydrogens.
Atoms are.
Does that help answer your
Well,
question?
because I was just wondering, like, why do one instead of the other? Is it random? Is there like consistent ways to get one instead of the other?
Like if you were making these things?
Yeah.
Yeah, no, definitely. If you were trying to make them, you would have to do a different process to get this than to get this.
And it's like one process will work every time.
Yeah, but it would be, in a sense, they would, even though they're made of carbon and hydrogens, yeah, if you did the reaction, you're only going to get one or the other.
Okay, so like a natural process would make the same one every time. The same.
Mm-hmm. Yeah, so that's like,
All this stuff is.
oh, okay. Like, if you guys ever go on and take organic chemistry, that's one of the big things you talk about is, okay, what reaction would I have to perform if I want the carbon to link on here and not keep making a chain? So, yeah, very good question.
So how do we know if we have C5H12 which one to make?
Oh, so in this case, because organic chemistry is not part of what you need to know right now, an example question would show you the Lewis structures.
Oh, perfect.
That's good.
Yeah, and that's a great point because symbol-wise, it would look the same. Yeah, so they would show you the Lewis structures, and then you would maybe have to like justify why this one has a higher boiling point than that one.
Okay.
So what would you say there? That was the question. Like, why does N-pentane?
Because N-pentane has a higher surface area. It's force.
Intramolecular forces or.
So there's greater interaction, so the dispersion forces are stronger,
Make greater interaction.
which makes more energy. So, any other questions with dispersion forces?
It's more energy.
So once you've identified that it's dispersion, the next thing I'd go to is weight, because that's easy. If weight is the same, then the next thing you go to is shape. Okay? All right, next type of force we have is known as a dipole-dipole. So a dispersion force, like we mentioned, is kind of like a fake polarity going on. This is when you actually have a polar molecule. So dispersion forces are present in non-polar, and then dipole-dipole forces are present in polar molecules.
Dipole.
Dipole. Why is it called dipole?
I'm guessing the dipole sounds like something Pokemon would say.
Which
Something of what?
What is
A Pokemon would say.
The reason it's called dipole-dipole is because remember the force is occurring between two different molecules, right? So this right here is a polar molecule. Why is chlorine the negative end?
Because it is
Chlorine's
being
more
strong. That is
More electronegative.
pulling.
Good, so it's greater electronegative, so the electrons are being pulled that way. Same thing in this molecule. So since this end of the molecule is a little bit positive, and this end is negative, that's where you get your dipole-dipole force. Because it's a dipole interacting with another dipole. So let's review really quick, because if I need to know if it has dipole-dipole, I need to know that's polar. So let's review, how do I know if a molecule is polar or non-polar?
If they're being
So if there's just two things, right, then you just look at the electronegativity, but normally it's more than two things, so say that one more time, Isaac.
You have to look at the symmetry of that.
The symmetry of it, right? If it's symmetric, then it's going to be non-polar, right? Such
usually
as,
if it has valence or like the lone pair bonds, then it's usually
Yeah.
polar.
so like methane, right? That's why it's a gas at room temperature, is because it's a non-polar molecule. Versus like ammonia,
Yes.
which is liquid at room temperature,
It's gonna be like forced together.
right? Because ammonia, like Ashton said, oftentimes when you look for that lone pair, it's causing it to disrupt the symmetry of it. So it's asymmetric.
What is the name of that?
That's ammonia.
No, like the structural name.
Oh.
Trigonal pyramid.
Pyramidal?
There it
Is
is.
it pyramidal?
Yep, trigonal. Because since this is here, that's why they go pyramid shaped
Tetrahedral
instead of flat.
is the,
Right.
Force.
is the
No, good review. Okay, so with dipole-dipole forces, being that it's now a true shift of the electrons, it's generally stronger than a dispersion force, right? Because of that. So if we notice here, the greater the polarity, the greater the force, right? So if we look at these different molecules up here, we see that they have about similar weights. But we notice the dipole moment that describes the polarity, that the greater the dipole moment corresponds to a higher boiling point, right? Because it's just making it a little bit stronger
Wait,
now.
what's the difference between dipole and dipole moment?
So the dipole moment is just describing, like, so, like, what do we have, I and Cl, right? So it's just describing, the dipole moment is describing this shift.
But
Oh,
then-
like how strong
did we
of the
go
shift
over
it is?
dipole
Yeah,
moments?
Yeah, how strong, it's a way, like, we've never calculated them or anything like that. You could, there's a way to calculate
Oh,
it.
don't you just do like the bigger one minus the little one?
Kinda, yeah, it's kinda like if you take the difference of their electronegativities.
So is dipole basically just polar?
Yeah, they're really just two words that, like, dipole describes the shift and then polar is used
Is
to
this
say what
chart
it is.
talking about polar molecules or non-polar?
Polar molecules. Because anything, well, the first one would actually be non-polar, as you can see, as a very, very, very low.
Oh, so it's like
So that's
the
just-
measure of the dipole moment.
So it's like
Yeah, so it's like the
polar.
strength of its polarity.
So it's like a descriptive word, like the dipole of this is like,
Yeah.
and this is polar.
And it is a polar molecule.
Okay, that makes more
Does that
sense.
make more sense? Those, but yeah, they really are like,
So this
whenever
one
you
doesn't have to
see
do with weight.
dipole, think polarity. Polarity, dipole, like they're connected.
This one doesn't have to do with weight, really.
Well, in this case, it's saying if they have similar weights, right, then it's really more to do with the polarity. If the weights were different, there is still that fact that the bigger it is, does make it a little bit stronger.
Even with polarness.
Yes, because the thing that we'll talk here in a second is that these forces are additive. So a polar molecule has dipole-dipole forces, but it also has dispersion forces as well. And so that's where when you get a heavier
that answers my
molecule,
question.
then that's why it can also influence it more.
Okay.
Yeah, so when we get to hydrogen bonding, anything that has hydrogen actually has the other two as well. We normally just focus on like, oh, this is the strongest, so we talk about it, but the other ones are also there. So, yeah.
So water's Kelvin would be 279 because its boiling point would be 0. Wait, no,
It's
that's freezing.
Melting or freezing.
Melting. So it would be 179 because of like if 100 Celsius is boiling, correct?
So
And-
water freezes at 273 Kelvin.
Okay. Okay.
Is that what you're asking?
Yes, yes, yes.
Yeah, 'cause you add, so then it boils at 373.
Okay.
Because it normally
Okay.
boils at 100 Celsius.
Yes.
Nope, you're good. Any other questions right now on dipole? Okay. All right, last one and strongest one, our good old hydrogen bonding. Okay, so like we mentioned before, but since Bradley wasn't here, is hydrogen bonding a true bond? Like when I say ionic bond, covalent bond, metallic bond, does that fall in those categories?
Yeah.
It does not. It's still an intermolecular force. It's still just interacting between two different molecules. Okay? So the definition, and I'll show you a picture here in a second, a hydrogen bond forms between an attraction of a hydrogen atom attached to a highly electronegative atom. So you're going to look for fluorine, oxygen, or nitrogen. Those are the only ones. So FON. However you want to remember it.
No.
Okay? NOF. That sounds more fun. Or that one. Okay?
Just, like,
And then
grabs
a
that
nearby electronegative atom of another molecule.
Just grab it.
Okay? And I'll show you a picture here. So hydrogen bonding is a special type of dipole-dipole, right? If it has hydrogen bonding, it's a polar molecule, but then it has this added strength due to the fact that when I take, so let's look at this here. So if I have hydrofluoric acid, HF, okay? Fluorine is extremely electronegative, right?
Yeah, it is.
So it's pulling the electrons away from hydrogen. But because it's hydrogen, if I pull its electrons away, what is it?
It's nothing.
Nothing.
Well, it's not nothing.
It's a little
It's just
proton.
a little
Just a lonely
nucleus.
little
Yeah, it's just a proton,
Oh, one
right?
What?
So what it does because of
Poor
this
guy, man. He ain't
is
got
you
nothing.
get like
Lauren's
an
taking
even
everything from him.
stronger, really almost full positive.
Oh my god.
Right, the electrons are sharing, so that's why they're not totally gone. But because fluorine is so much stronger, you get this really basically just a proton hanging out there. And then this is really, really negative. And then in result, this can interact with another fluorine.
42.
Of another one.
So what is something that involved with the F and the H like that?
Say that again.
So the F and the H, like what reactions that happen in real life? Like Does it ever react with each other often, or
Like these things?
yeah,
Like, do they have a bond?
do they have a bond often, or
Yeah, hydrofluoric acid exists.
okay?
Yeah.
Hydrofluoric
Doesn't this
acid.
mostly happen in water? Hydrogen bonds?
So yeah, that's the one thing we want to talk about is there's hydrogen bonding in water. And that's a key thing there. So notice that when, in order to say something's a hydrogen bond, okay, it has to have a fluorine directly bonded to it, or nitrogen or oxygen, one of those three. Okay, it has to have a NOF bonded to it, and then it's an intermolecular force between another NOF. So you kind of have to have this sandwich in order for it to be considered a hydrogen bond.
Oh, and water has oxygen.
Yeah, so if we draw water out,
Wait, so water's covalently bonded and then it has a hydrogen bond on top of that attracting intermolecularly?
yeah, so we have water here. So oxygen's pulling the electrons towards itself. Right, so like Isaac said, this is just the covalent bond within the molecule. But then if I have another water molecule, how's it going to interact with this?
It's the O is gonna be like attracted to
Yeah,
the
so we're
H.
going to get this intermolecular force of another water molecule.
It's gonna be a good one too, man.
Yeah, and it's going to be like a really strong force, right? And it is crazy, right? Notice hydrogen bonding. It's not a true bond. It's weaker than the covalent, right? I can break this by melting. I don't break this by melting. But hydrogen bonding literally keeps us alive. Like if water didn't hydrogen bond, think about this, ready? Because water hydrogen bonds, it causes ice to be less dense than water. Because what happens is you get these interactions and you get a crystal structure because certain things don't want to get next to each other and other things do. And that's how you get really cool snowflakes, is because of hydrogen bonding. But why is that so important? What would happen if ice was more dense than water?
Then it would sink and then freeze and then sink, and then we would just have oceans of pure ice.
Yeah, if ice didn't float, lakes would freeze from like the bottom up instead of just being on the surface. Because as soon as it would form, it would sink, right? And then just again and again and again.
And it would kill all the fish, because the fish would be trapped under the ice and it would just smash them.
Smash the little
Does
fish.
that happen?
I mean, theoretically, probably. Or they'd all run out of oxygen and water.
You know?
You know, and it just would never be able to melt, right?
So does this ever happen with
But ice is-
non-chlorine
but our
oxygen?
oceans
It says
don't freeze.
usually.
No. Hydrogen bonding, we're just going to say, is with nitrogen, oxygen, and fluorine. No, great point, though.
And then it would sink to the bottom and never melt. 'cause it's-
Other questions on that, on hydrogen bonding? And we'll talk about some of the other really cool things. Hydrogen bonding also keeps us alive because water is polar, right? And we're like 70% water. Water is what allows our body to transport different minerals because the water can grab onto those positive and negative ions and deliver them. If water was non-polar and didn't have those forces, yeah, it wouldn't carry anything anywhere, right? Okay, so these are all different examples of how a hydrogen bond can exist. So in this picture, where is the hydrogen bond though?
The red dots.
The red dots, okay? That's key. The other ones are covalent bonds. So notice that the hydrogen bond has to exist with the hydrogen truly bonded, and then that's the hydrogen bond. But you have to have a NOF on both sides. And notice that it doesn't have to be the same one, right? So like in this one, it's truly bonded to an oxygen, but then it has a hydrogen bond with a fluorine.
So it has to be an F and O or an N.
But it has to be an F or O and an N, and it's truly bonded to one, because why is that important? What's the true bond causing?
Because then it's pulling
That's
the
what makes it
electrons
so
away from
polar.
that hydrogen.
So then it can latch on to this other one. Okay? All right, so this other type of force we have only exists in solutions.
Oh, back to solution.
Yes, but just this tiny little, this is all we have, one sentence on solutions right now. So the force in solutions, and we've talked about this force before, but now we're just giving it a name. It's known as an ion dipole force. Okay, so we've talked about this force that when salt dissolves in water, the water molecules form around it in different orientations, right? Since this is since this is negative, all of the positive hydrogens form around it. And then since this one is positive, the negative oxygen atoms form around it. So that's why it's called an ion dipole force. Okay? And it is actually quite strong. I mean, if you think about it, it's strong enough to pull apart salt. Right? As long as it's staying surrounded by it. So, okay, so this chart kind of compares all of our different forces and their strengths. So notice that dispersion force is the weakest, but there is some overlap with dipole-dipole, right? You could have some weak dipole-dipole, and dispersion actually is stronger, and we'll see some examples of that. Then we see that we have hydrogen bonding, and ion dipole is actually way up there too, but that only can happen if you're talking about a solution. So most of the time we won't really deal with that in this chapter. And then notice how big of a difference it is when we go up to ionic and covalent bonds. Right, that the force for those is a lot stronger than just our intermolecular forces. Right? But
And that
maybe
like
some
jumps,
of you...
That's huge right there, because that's 4,000 to
yeah,
1,000.
the scale
and that's only,
changes like crazy.
It's only like 50 to 25, and all of a sudden 400 to 1,000.
Yeah, they didn't really make the scale like to scale.
Up there,
1,
dude.
2, 5, 10, 1,000.
Yeah, that makes sense.
Perfect.
Thank you. Just give me
But some of you maybe have had a personal experience with the strength of a hydrogen bonding if you've ever done a belly flop in a pool before.
Please explain.
Surface tension.
So, and we'll get to this a little bit more, but yeah, so because those water molecules are grabbing on to each other, right? So across the surface, oh, well,
Big hydrogen bond.
oh, forgetting my dots. True bond. Okay, so across the surface of a pool, the way I think about it is the little water molecules are kind of like all holding on to each other.
They're like, no, it's like Red
Red
Rover. Red Rover.
There you go, Red Rover, but like in three-dimensional
They're trying to
space.
stop me from getting there.
Alright, so there's this
If you make
3D
a point, it's easy to go through because then you just like
Red Rover,
all your energy's
right?
focused, but if you
So the
stretch-
water molecules are hanging on, and this is what is known as surface tension. So why it hurts when you belly flop is because if you hit it like this, you don't break the intermolecular force.
Oh.
And so you feel it.
Wait.
If you break it like this,
Well, you break it eventually. It's just
well, yeah, you break it eventually, but you feel the force before you break through it, right?
if you do that.
So the whole goal now that we know our three types
That's cool.
is to now relate them to these properties like surface tension and other things. So kind of here's a breakdown of what you want to look at is that when when molecules of two substances have comparable weights and shapes, then normally dispersion forces are equal. So the thing you'd want to look at is their polarity of what affects it, right? So if they weigh the same and they have a similar type shape, dispersion forces wouldn't really be different between them. So see if there's a difference in polarity, and that will normally explain why one is greater than the other. On the other hand, if their weights are really different, and there's no hydrogen bonding, then this is where actually dispersion forces could outweigh the dipole-dipole force. Is if you have something that's like really, really heavy, you could actually see a non-polar have a higher boiling point than something that is polar. So that would be your justification. And that's what you're going to be doing here is like, it's going to be more of the fact that they'll show you a trend and your job is to explain why it is, right? They're not going to be like, tell me the boiling point of alcohol, right? They're going to show you the boiling point of alcohol. They'll show you the boiling point of water, and you have to justify why they're different from each other. Okay? Oh, and remember, like we mentioned before, that they are additive properties, right? Anything that has hydrogen has dipole and has dispersion. Okay, so here's kind of a flow chart. It helps as you're trying to identify. So if you're trying to figure out what force is present, the first thing I always look at are ions involved. If ions are involved, if it has positive and negative, then the next thing you look for is it in solution or not. If it's not in solution, then it's just a true ionic bond, right, which would be very, very strong. Okay? If it's in a solution, then it's that ion dipole force. Then, if the question is no, it doesn't have ions, then the first thing I always look for is polarity. If it's not polar, then it must be dispersion. If it is polar, then you look for hydrogen bonding. So that's kind of the breakdown.
Okay.
So let's try this problem. So the question says we want to list these substances in order of increasing boiling point. So what is the question within this question?
Intermolecular forces.
So intermolecular forces, and so if the boiling point is increasing, what does that mean about my intermolecular forces?
It's lowest.
We want lowest to highest, or weakest to strongest. Okay? All right, so let's go through these and just identify what forces are present. So we have BaCl2.
Additive.
What force is present in BaCl2?
Ion.
It's just ionic, right? This is actually just an ionic bond. So I know in my list, most likely, where will that be?
The top.
At the very highest, right? Because that's a true bond. There's not really those other forces going on. Okay, H2, and for some of these you might have to draw out Lewis structures if we need to see symmetry or not. But for H2, what force is present? Good, just dispersion because it's nonpolar. Okay, let's see, CO, what would that be?
Covalent.
So it's covalent. So now is it polar or non-polar?
It is polar.
Why is it polar, Justin?
Because the carbon pulls on the oxygen. Or
Other
no,
way
the
around.
oxygen pulls on the
There you
carbon.
go, yeah. But yeah, because they're just two things bonded, and the oxygen has a different electronegativity, so this would be dipole-dipole.
Can we just call it double D?
Double D. Sure. I mean, if you're just doing work, it doesn't matter, right? They just care about your final answer.
Wait, with BaCl2, like when we're looking at boiling point, aren't we looking at the intermolecular forces, not the intramolecular forces?
Yes, but that's what's interesting about, remember with ionic bonding, right? So ionic bonding is you have positive, and then you have your negative bonded like so,
Yeah.
right? But in a compound of BaCl2, right, what you have is you just have another Cl bonded to another Ba, bonded to another Cl. Bonded to another Cl, bonded to another Ba, bonded to another Cl. So even though, like, it's in a sense that its real bond is almost its intermolecular force as
Okay.
well. You see that?
Mhm.
But really good question. Okay, what's present in HF? Hydrogen
Hydrogen
bonding.
Oh,
Okay, be careful with the hydrogen bond that just because it's an H doesn't make it a hydrogen bond, right? You have to look for N, O, or F. And then what would neon?
That's nothing, right? It's not bonding with that. It's not even.
So if it did have any force, it would be dispersion.
Because it doesn't like.
Because it can still, if we force neon to be a liquid, which you could, right? Then it still could have that slight shift, even though it is just a single atom. You could have that shift of where the electrons are shifted to one side, and then it could be influenced. But yeah, you're totally right. In this case, like it's a very, very low dispersion, which recognizing that, which one would probably be the weakest?
Neon.
Yeah, neon's going to be the lowest of our list. And obviously it has a really low boiling point because it's a gas. What one would come next?
H2.
Good, our other dispersions, that's going to be less than H2. Okay, then our next one would be
Probably CO.
our CO, because that's dipole-dipole. And then what would we get? HF, because hydrogen bonding. And then our ionic. Very good.
Okay.
Questions on that? Okay, let's have you try the next one on your own, and then we'll check it for some smiley faces. So list these four substances in order of increasing strengths of intermolecular forces. So let's go through the forces. What's present in argon?
Dispersion.
Dispersion.
Dispersion. Okay, what's present in Cl2?
Dispersion.
Just dispersion. CH4.
Dispersion.
And then what's present in that?
Double D.
I just figured if it's not dispersion, then it's bigger.
So it is polar. How would I know this is polar?
Because it's very complicated.
It doesn't
It's
look
not
very
symmetrical.
symmetrical.
That's what I would go off. Is like looking at this, it's not symmetrical because there's more oxygen on one side, but we have a deeper level because we actually have hydrogen bonding.
Oh, what?
Oh yeah.
Because you have an O bonded to an H.
Wait. Oh, but even though the C is in there, just because you have an O to an H, that makes it a hydrogen
yeah, because
bond?
on that's going to be the edge of the
Okay.
molecule, and so then that can
Okay.
influence.
I just
Either
thought-
way, you actually could solve this one because all the rest are dispersion. So I know that this should be the greatest, right? So then how do you decide the other ones?
You take a
Oh.
guess. Smallest, biggest.
Argon is
Three,
like
just
the
throw
amount.
'em on
Argon
there.
is
the
very
electromagnetic
is gonna be the
emissivity,
smallest.
but it's the atoms.
Good, so argon should be the lowest because it's just a single atom.
Silver.
Silver.
Silver should be the lowest. Just kidding.
It's not even-
Argon. Okay, so then how do I decide between these two? I heard the debate, but what do I do?
Electromagnetic one's bigger.
I thought
Yeah.
CO2
Smaller
because
one should be
it's
closer to
bigger.
Say that one more time.
The smaller one should be closer to argon.
Yes, so with dispersion forces, if they're both dispersion, the next thing you go to is mass.
Mass. And that's CH4.
So CH4 is
Oh.
lighter.
It
It has less of a dispersion force than chlorine.
Oh, because Cl2 is heavier than CH4.
Yeah. So with dispersion forces, if they're both present, then the next thing you go to is weight. If my weights were the same, then what would you go to?
Then to
Shape of it. Yeah, how the shape of it is
surface.
structured.
So if say those two had the same mass, would you do CH4 just because it's bigger surface area?
So the
If their weights were the same?
that would be hard if they weighed the same because those would be somewhat comparable.
I'll just put equal sign.
Yeah, that would be really hard for those two.
Well, they're not. Okay.
It doesn't because carbon's not that electronegative.
Oh,
So that's why, it's because it doesn't cause that great shift. So, yeah, but great point to bring up. Okay, so another thing that this explains is why a substance is what we know as viscous. You don't know what viscosity is?
Yeah, it's resistance to flow.
Yeah, resistance to flow is the technical way to talk
So
about
like
it.
honey.
I talk about like it's the thickness.
Stubborn people.
Stubborn people. These are the stubborn liquids.
Now, what makes something sticky?
That's another part, but it's kind of related.
Sugar.
So something that is viscous, it doesn't flow very easily. Would that have high or low attractive forces? Excuse me.
High.
Why would you say high? Yeah, because they're grabbing onto each other, right? Obviously, because some people probably think about, well, water. Water has strong forces, but it's not viscous.
It
Right?
does have strong forces. Oh, because hydrogen bonds.
But it's just, often it deals, one, with the attractive forces, and also this idea of the molecules getting entangled with each other. So lots of times the shape of it, yeah. So I
Some
think
big
about it,
shapes.
it's like if you have molecules that can kind of like grab on in a lot of different ways because they're really big, like really big long chains like spaghetti, and they can get intertangled.
And fats are viscous because fats are really
Yes, and fats are really long chains, so that's why they
Good
don't
morning,
flow very
pumpkins.
well.
Here